exponential decay graph looks like. It starts high and then declines over time. But notice that that x-axis is still an asymptote. I mean, there's no way, because we're starting off with a positive value and our base is positive, that we're ever going to get anything that's negative. Those values are just going to get smaller and smaller and smaller and just keep getting closer and closer and kind of like hugging that x-axis. Okay, let's go ahead and turn the page. Okay, so this question asks us to tell whether the function shows growth or decay. So we have to decide, is this growth or decay? And we just looked at in that table that what determines whether the situation is growing or declining or decaying is whatever the base is and its value relative to 1. And so if you look at the base here of this exponential function, it's 3/4. And 3/4 is between 1, it's less than 1 but greater than 0, and so this is definitely a situation of decay. Now secondly, they want us to graph the function using a table of values. So the first thing we would do is determine appropriate x values, so pick some nice x values, and then plug into the graphing calculator and use the table feature to fill in the chart. Well, since the graph here only provides me with the first quadrant, then the x values I think I'm going to choose are going to be positive values. Otherwise, it would be something off my graph. So I'm going to say put in 0, and maybe to get a good look, since my graph goes all the way up to 11, I might maybe go 0, and then maybe I'll go to 2, and then maybe 4, 6, 8, and 10. Now I could have gone up by 1s and then just put more points on there, but that's a pretty good listing of points, and then at least I'll fill up this table that I've got here, this the coordinate plane. And so I could put this in my calculator, and I could just look at the table. So when I typed this into my y equals menu and I went to the table function, I could see these values. So I can just go ahead and fill them in my table. So if I were to substitute in 0 into that 10 times 3/4 to the x power, I get 10. And that's because 3/4 to the 0 power will be 1, and 1 times 10 is 10. And then if I substitute in 1, I'd get 7.5. Well, that one's not on in my table, so 2 is 5.625. So I'm going to approximate that at about 5.6. And the next one I have in my table is at 4, so that'd be about 3.2. And the next one is 6, which is about 1.8. And when you can't see on the table is for an input of 8, and that's about 1.0011, so that's about 1. And then for 10, it's about 0.56. So if we were to plot these points on the graph, at 0 we would plot 10, at 2 about 5.6, so we could approximate that right around here. At 4 it's about 3.2, maybe right in there. 6, 1.8, so just below 2. Maybe right in about there. And then at 8 it's 1, and 10 it's about just close, a little bit over a half, so maybe right in there. And then to connect them, they're actually going to make a curve, so maybe something like that. Now remember, the x-axis really represents this asymptote, so like this graph cannot drop below this line here. And so basically what we do is once we get to this point, we just sort of have it taper off going towards that x-axis, but sort of kind of flattening out. That's just showing it's not really crossing it, it's just approaching it but never really getting to it. And if you actually were to hit graph on your graphing calculator, you could see this curve too. Of course, you're probably not going to see it in the same window that I have here, because most likely you're in a standard window, which is -10 up to 10, but you can still see the general shape of this curve. All right, let's go ahead and turn the page. Okay, so here's another one, and we want to know whether this represents growth or decay. So remember, we look at the base, and we can tell if it's growth or decay by what interval it lies in. So the base, the thing that's being raised to the power, is 1.05. And so this one is representative of growth because it's greater than 1, and so every time we multiply the original amount, which in this case is 100, and we multiply by 1.05, it's going to grow, it's going to get bigger. And then we take our new value, multiply by 1.05 again, and it's going to continue growing. So that's exponential growth. Now this time we're going to prepare to graph this function, but we're not actually going to graph this because clearly this would be, a fairly large graph. We've got to start at 100 and then we're growing by multiplying by 1.05, and so they would get very large numbers. So, but if I would put this in the y equals menu and I just went to the table and I picked some values to plug in, say maybe I'd put in for values for x is -2, 0, 2, 4, 6, and 8, and you can feel free to type this in your calculator and fill the table in on your own, or just take a look at my values. When I put this in, I got for -2, I got 90.7. Now that makes sense, because that's like saying if I put in a -2, it'd be like it's going back to. So if it's growing going forward, then it would have to be declining going back. And so that number is smaller when we plug in 0. So it basically at time 0, it would be 100. If we plugged in 2, it would be 110.25. At 4, the table shows 121.55, so about 121.6. At 6, 134.01, so maybe just put 0.0. And then for 8, it's 147.75, so we'll say about 147.8. Now, oftentimes when we talk about exponential growth or decay, we usually are talking about something growing by a percentage. Like we'd say, like the population in this city is growing by so many percent, say 5% per year or whatever. And so this following formula is a formula that's just tailored more towards if things are growing by a percent instead of like doubling or tripling or whatever. And the way it works is this. A of t means the amount at a specific time t, and it's equal to A, which is an initial amount or starting value, times 1 plus or minus r raised to the t power. Now, why the plus or minus? Well, the plus and minus means that if you're adding the r, which is r is the rate of increase or decrease, so it'd be a percent, and you're adding it to 1. Well, what does 1 mean? Well, 1 means 100%. So when I look at that 1, it really means 100%, but as a decimal, plus the percent of growth or decay. So that really, when I take 100, I change it to a decimal, it's really 1, and then plus whatever that increase is. So let's say, for instance, I had a growth of 5%, so it would be 100 plus 5%, which would mean, as a decimal, 100% would be 1, and 5% would be 0.05, and if I added those together, that would be 1.05. So multiplying by 1.05 would model growth of 5%. Now, the reason why there's a minus there is it could be declining. So if something was declining by 5%, instead, it would be 1 minus 0.05, which would leave me with 0.95. And if I was multiplying by something like 0.95, which is between 0 and 1, it's going to be declining. So that would be causing a decrease. So again, the plus means growth. So if I'm adding a percent, that's growth. If I'm subtracting a percent, that's decay. Let's go ahead and turn the page. Okay, so we're going to wrap up this lesson by looking at a couple of real-life examples, because isn't that exactly why we study mathematics, so we can apply it to real life. So in 1981, the Australian killer whale population was 350 and was and increased at a rate of 14%. Well, that's good to hear. It's increasing by a rate of 14% each year since then. Use a graph to predict when the population will reach 20,000. Well, first of all, the first step is we need to determine if this problem is representing growth or decay. Well, clearly it says it is growing. It's increasing, so it's saying it's growth. So we know it's growth, and we want to write the general formula. Well, if it's growing by a percent, we can use that general formula that A of t, amount at a given time t, is equal to initial value of A times 1. And in this case, we're going to use the plus r because it's growing and raised to the t power. Well, so let's see what values are going to go in here. A means the initial amount. This right here is the initial amount, the 350. That's what they're starting with. And it's being multiplied by 1 plus, and then the rate of growth as a decimal would be 0.14, 14% as a decimal, and then raised to the t power. So this would be our function that models this growth situation. Now, usually if we wanted to know, when the population would reach 20,000, and we wanted to just go ahead and plug in say a value right here for the amount of 20,000, and then we'd say, okay, well, how about if we just solve this equation? And we would find out what t is, and that would tell us how many years. Oh, and by the way, I guess if you wanted to, you can rewrite this. Instead of writing them separate as 1 plus 14%, you could write it as 1.14. But we don't actually know how to solve to find out what t is. We can't solve an equation when the variable is in the position of an exponent. That is something we will learn at some point in this chapter. In fact, that's why we're going to be studying what are called logarithms. But for now, the best we could do is we could plug in values of t and keep plugging in until we get close to 20,000 and approximate it that way. Or probably our best bet is, since we do have the technology of these graphing calculators, is we can go ahead and put it in our calculator, and we could either trace the graph or we could just go to the table and look for when we get to 20,000. So that would really be our best bet, is to just go ahead and put this function in. So we're going to put this right here, our function, put that in. And instead of using t in the calculator, we'll just use x, and then we can go to the table and see what happens. So I just put this in my graphing calculator. In the y equals, I put 350 times 1.14 to the x power. And now I've gone over to the table, and I'm just kind of scrolling down the table, and I'm already to 28 years, and I'm up to 13,722. So if you're following along, we got to keep going in the table. And so when I got to year 31, at year 30, it was 17,833, and when I got to year 31, it was 20,329. So it's going to be just less than 31 years. So what that means is, if we started at 1981 and it's 31 years after that, then the year when it's going to reach 20,000 is around 2012. So we could go back and look at data for 2012 and see if that ever happened and if this growth rate continued. And that's a pretty big assumption. And there's so many other factors that come into play, environmental factors, and they're predators and all that. But if there's a sustained growth of that over a period of time, then it's safe to predict that, at least for the short term, I don't know if 31 years is short term, but in the short term, that's going to continue to be the case. So let's go ahead and turn the page and look at one final example. And this final example we're going to label as a you try in class. So this is going to give us a chance when we're in class together to try one in class. So if you're having any trouble, I can be here to support you, but I just wanted to let you know so that you don't have to try this one on your own. We're going to label this as a you try in class. So this is what we'll start off our next class together with. So I will see you then.